Scientific notation is a way of writing numbers that scientists might use if they need to talk about very large numbers, like maybe distances between planets, or if they need to talk about very small numbers, maybe if they're talking about cells in biology. In order for us to write numbers in scientific notation, it's really important for us to understand how those powers of 10 work. And you'll remember from previous lessons we talked about things like 10 to the 4th power being equal to 10 times 10 times 10 times 10, where that exponent tells us how many times we are using 10 as a factor. So 10 to the 3rd would be the same as 10 times 10 times 10, or 10 being used as a factor 3 times. And then by pattern we know then that 10 to the 2nd would be 10 times 10. And 10 to the 1st would just represent 10 to the 1st power, or sorry, 10 being used as a factor 1 time. Okay, so that becomes very important in scientific notation because we use these powers of 10 to help us express these large or small numbers. It's also important for us to remember how those negative integer exponents work. And if you'll recall, we talked about how a negative exponent tells us to take the reciprocal of the base that we see. So 10 to the negative 1 would be 1 over 10 to the 1st. Well, if you remember, fractions are really representing division problems. So that very fraction that we just wrote means the same thing as dividing by 10 one time. So 10 to the negative 2nd, or that would be 1 over 10 to the 2nd, or 100, that's the same as dividing by 100, or dividing by 10, and then dividing by 10 again. So 10 to the negative 3 would tell us that, yes, we're taking the reciprocal, so it would be 1 over 10 to the 3rd, but that means the same thing as dividing by 10 3 times. So if we follow that pattern, we know then that 10 to the negative 4, well, that's the same as 1 over 10 to the 4th. That means,
have a custodian to the main office?
Uh-oh, they need a custodian in the office. 1 over 10 to the 4th would be the same thing as dividing by 10 4 times. Okay. Now, the other thing we need to review before we really dig into this scientific notation is what it really means when we shift decimals. What does multiplying by 10 look like in terms of the change of the number? So let's take a look, for example, if we want to multiply 2 by 10. We know that 2 times 10 is really 20. And if we write that out showing the decimal placement, we notice that the decimal goes from being right behind the 2 to making one shift over. So now we have the decimal one space away from that 2, or one digit away from that 2. So we wanted to take something like 45 and multiply it by 100. Remember, that's the same as 45 times 10 times 10. Well, we can take that decimal, and every time we're going to multiply by 10, we can do a decimal shift to the right. That one shift means times 10, and then the next shift would be another times 10. So we can very easily rewrite 45 times 100 by just shifting the decimal place two places to the right. So this would wind up being 4500, or 4,500. So again, every decimal shift to the right means we're multiplying by 10.
Kevin Anderson, please call Cindy at 57102.
So let's talk for a minute about what it looks like if we divide a number by 10. So if we take 30 and divide it by 10, instead of moving the decimal once to the right, this time we're moving it once to the left. So you know that if we have $30 and we share that between 10 people, each person's going to wind up getting $3. So there again, you can see that one shift from the right to the left this time, and that means that represents division by 10. If we want to divide by 100, we're simply going to shift that decimal to the left 2 times, because dividing by 100 is the same as dividing by 10 and then dividing by 10 again. So we would take our 921, but instead of leaving the decimal after the 1, we're going to do a shift once for dividing by 10, twice for dividing by 100. So that decimal winds up right after the 9, between the 9 and the 2. Understanding how dividing by 10 and multiplying by 10 is represented by a shift in decimal placement makes it easier for us to work in scientific notation. Now, in scientific notation, there are some specific rules we have to follow. And the first rule is that no matter what number we're initially talking about, we are going to represent it with a number that is between 1 and 10. So we can have 1, we can have it equal to 1, but we cannot have it equal to 10. So a mathematician might write that statement as, our number has to be greater than or equal to 1, but it has to be less than 10. And then we're going to take that number that we use that's between 1 and 10, and we're going to multiply it by a power of 10. So there are 2 parts to scientific notation: a number between 1 and 10, and a power of 10. So let's look at some examples and do some of these together. Let's say we want to talk about the number 325,000, and we want to express that in scientific notation. Well, let's take all the series of non-zero digits. So we're going to look at the 325. So we know that that's our first number. Now, you and I both know that 325 is not equal to 1, and it's not between 1 and 10. So we need to do a little bit of decimal movement here. Our decimal in 325,000, remember, is after the ones place. It's right here after that last 0. And in order for us to use the digits 325 and get a number between 1 and 10, we have to move that decimal. And we know that if we need this to look like something between 1 and 10, we need to put the decimal right here, because 3 is between 1 and 10. But there's a big change in decimal placement from the original number. We actually had to shift that 1, 2, 3, 4, 5 times. So remember, every decimal shift is a multiplication or division by 10. Now we have to think about this because it doesn't come naturally to us. Our original number was 325,000, but right now we're looking at 3 25/100ths. Well, 325,000 is larger than what we are looking at in the 3.25. So our exponent on our 10 is going to be a positive integer. In this case, it's going to be a positive 5, because we had to shift the decimal 5 places in order to get from 325,000 to 3 25/100ths. So remember, this exponent tells you how many times we've shifted the decimal, or multiplied or divided by 10, to get from our number into scientific notation. It does not represent the number of zeros you see in the original number. So let's do a couple more examples to gain some comfort on this. The practice that we're doing right now is taking a number from standard form to scientific notation. So let's start with 4,000. And we need to start with a number that's between 1 and 10. So in order to get that, we're going to take this 4. And we know that 4 is between 1 and 10. So we're going to use 4. I'm going to go ahead and put this decimal in so that we can see the number we're talking about. We know we're going to be multiplying by a power of 10. In scientific notation, you never have another base. It's always powers of 10, because that's the base that our number system is built on. All right, the original decimal in 4,000 is after this third 0. It's after the ones place. And in order to get from 4,000 to 4, we had to shift that decimal 1, 2, 3 times. So that means we are going to multiply 4 by 10 to the third in order to get from 4 back to 4,000. The next number we're looking at is 7,300,000. So we know we're going to take these non-zero digits, the 7 and the 3, and that becomes the first number in our scientific notation statement. And we know to get 7 and 3 between 1 and 10, the decimal has to go right here, so that gives us 7 and 3/10. But the original decimal, remember, was after the ones placed in 7,300,000. And that would place the decimal here. Well, that means we had to shift that decimal 1, 2, 3, 4, 5, 6 times in order to get to 7 and 3/10. So that means we're going to have 10 to the 6th power for this particular number. So 7,300,000 is represented by 7.3, or 7 and 3/10, times 10 to the 6th in scientific notation. All right, let's do the next one. That is 63 billion. That's a very large number. It's a lot of zeros. It's very easy to get lost in the zeros in this number. So let's put this in scientific notation. All right, we're going to take those front numbers, the 6 and the 3, and we know to get this between 1 and 10, the decimal has to go here, so we have 6 and 3/10. Now there's a lot of decimal shifting here. There's a lot of multiplying by 10 to get from 6.3 to 63 billion. So we're going to start with the decimal in its original place, and we're going to count over. There's 3 shifts here, 3 more shifts here, 3 more shifts here, and 1 more. So that is 10 shifts of that decimal, or multiplying by 10 times to get from 6 and 3/10 to 63 billion. All right, 230,000, that's not quite so bad. But the same practice follows. We're going to take those front digits, we're going to take 2 and 3, and we're going to make that 2.3 because 2 and 3/10 is between 1 and 10. And we know because scientific notation is always multiplying by powers of 10, we can go ahead and put that base in. The original decimal is after the ones place in 230,000. And to get from there to 2 and 3/10, we had to do 1, 2, 3, 4, 5 decimal shifts. So that tells us we're doing 2 and 3/10 times 10 to the 5th. All right, a couple more here. We have 2,420,000. And we'll, again, always starting with those non-zero series of digits. So we're going to have 2, 4, 2. And the decimal is going to go right here because we need a number between 1 and 10. Now, in order to get from 2 and 42/100 back to our original 2,420,000, we had to multiply, we'll have to multiply by 10. 1, 2, 3, 4, 5, 6 times. So that means 10 to the 6th power. All right, last one, kind of an easy one down here. That's just 105, but we can even take numbers like this and express it in scientific notation. Now we're going to take, because this 0 is in between our non-zero digits, we're going to include that. So we need 105. And remember, our number needs to be between 1 and 10 or equal to 1. And the only place that the decimal can go for us then is right here. So we have 1 and 5/100, just a little over 1, times a power of 10, because this is scientific notation's rule. And in order to get from 1 and 5/100 to 105, we had to move that decimal once, twice, or we would have to multiply by 10 to get back, or I'm sorry, multiply by 100 to get back to 105. All right, so everything we've done this far looks at numbers that are larger than 10, big numbers that we're condensing down for scientific notation. We can also use this idea for very, very small numbers. So for example, if we look at this first number, we are looking at 475 hundred thousandths. That goes out quite a ways. That's very, very tiny. We can use the same ideas to express these tiny numbers in scientific notation too. We're going to keep to the same rules. The first number we're using has to be between 1 and 10. So we're going to take the 475. And the decimal would have to go between the 4 and 7 to get us between 1 and 10. We're still multiplying by a power of 10. But in this case, 4 and 75/100 is larger than the number we're talking about. So we would actually have to shift the decimal left, or we would have to divide 4 and 75/100 to get to these smaller numbers. So in this case, the decimal shifted 1, 2, 3 times. But because, again, because our original number is smaller than 4 75/100ths, by the way, that should be, let me rewrite that because that should be at times. We are going to use a negative exponent. So because we shifted 3 places, we are going to use -3. Remember, that -3 is the same as dividing by 10 3 times, which is exactly what we did when we shifted the decimal to make a smaller number. All right, our next example, I'm going to use the 526, and that decimal has to go after the 5 to get between 1 and 10. We're multiplying by a power of 10, and in this case, to get from 5 26/100ths to this very tiny number, we have to shift the decimal once, twice, 3, 4, 5, 6 times. So this would be 5 26/100ths times 10 to the -6. Now remember, that negative is telling you that you're talking about a number that is much, much smaller than 5 26/100ths. All right, the next example, we're going to keep that 8 and the 2. We need those to start our scientific notation. We need to get that between 1 and 10. We're going to multiply by a power of 10. And in this case, the decimal is shifting 1, 2, 3, 4, 5, 6, 7, 8, 9 times. 1, 2, 3, 4, 5, 6, 7, 8. Yes, 9 times. So this would be 10 to the -9. That negative is indicating we're talking about a tiny number here. All right, we've got 237 10,000ths. So we need 2.37. We're between 1 and 10. Multiplying by a power of 10. And in order to get from 2 37/100ths to this little decimal, we would have had to have shifted the decimal twice, or divide by 10 2 times. All right, and then next example, we're going to take the 9 and the 7, so we'll have 9.7 times a power of 10. And in this case, the decimal is going to move 1, 2, 3, 1, 2, 4, 5 times. So this would be 10 to the -5th, -5. Okay, one more example and then we will wrap this up. In this case, we have the 3141. We're going to get that between 1 and 10 times a power of 10. And in this case, we are shifting 1, 2, 3, 4 times. So this will be 10 to the -4. Okay, so remember, if our exponent on our 10 is positive, we're talking about a number that's larger than this first number in scientific notation. If we're talking about a negative exponent on that 10, we're talking about small numbers. All right, what happens if we need to take a number from scientific notation to standard form? This isn't really so bad after all. We're going to write down the 3 and the 5. Those numbers don't change. But that 10...
Dr. Krischer, the substitute is here that you're looking for?
It's a busy place here at Northeast Middle this morning. So this 3, this exponent, tells us how many times we need to shift the decimal, not how many zeros we need to write. How many times does the decimal shift? Well, the decimal was originally between the 3 and the 5. So we're going to shift it once. We're going to shift it again because we have 3 shifts to make, and one more time. And every time we shift, we're going to have to put a 0 in for placeholders. Okay, so this number, 3.5 times 10 to the 3rd in standard form, is really 3,500. And remember, the decimal's right here after the ones place, so you can see where that decimal has shifted. Okay, and I'll remind you again, the exponent on the 10 does not tell you how many zeros to write. It tells you how many times to multiply or divide by 10. And it looks like a decimal shift, not just a 0. So our next number, we have 2 48/100ths times 10 to the 6th. So we're going to write the 248. The decimal was originally between the 2 and the 4. So we're going to shift 10 times. We're going to multiply by 10, 6 times, sorry. 1, 2, we'll need to do it again. That would be 3, 4, 5, and 6. Oh, that's way out there. And so that decimal is going to wind up over here. So let's double check from between the 2 and the 4. Times 10, do it again, that's twice. 3, 4, 5, and 6. Okay, so this number in scientific, or out of scientific notation and into standard form is 248. Okay, remember, put your commas in. It makes it a little easier to read your number. So this is 2,480,000. Now the next example, we have a negative exponent on our 10, so that means we're going to be dividing by 10 several times. We're going to be shifting the decimal left. So it helps to give yourself some space here. We're going to write the 5 and the 1. Now the decimal was originally between the 5 and the 1, and we need to shift left. We need to divide by 10 4 times. So we are going to go from the 5, between the 5 and the 1, we're going to divide by 10 once. We need to do it twice, 3, 4 times. And every time we shift it, if we don't have a digit, we need to put in a 0. So we're going to have a 0 here, here, and here. And that's where our decimal goes. Now we're going to clean this up just a little bit. And we're going to go ahead and put a 0 in the ones place. And again, this is not counting zeros. We have counted division by 10 or decimal shifts. Okay. And then the last one. 9 and 1600ths times 10 to the negative 2. That means we're going to take 9.16, and we are going to divide by 10 twice. So 916. Let's clean that up a little. The decimal was originally between the 9 and the 1, so we're going to shift the decimal from here. We're going to divide by 10 once. We're going to divide by 10 twice. We need to throw in some zeros as placeholders. And that's where our decimal goes. And then we'll clean it up. Always a 0 in the ones place if you don't have another digit. Okay. And so we've practiced taking numbers at this point from scientific notation to standard form for both the larger numbers and the smaller numbers. Probably not a bad idea to review your notes. Make sure you have written down everything you see in this video so that you have a lot of examples going from standard form to scientific notation for both large and small numbers, and going from scientific notation to standard form for both the large and the small numbers.